Hey there, Enclosure fans. Welcome back to the Enclosure Institute, brought to you by your friends at Marian Incorporated and Rogers Corporation. I'm Phil Taylor.
And I'm Jimmy Budd. Last time we talked about some of the important considerations that can affect the material choice for your enclosure gasket. Today we want to discuss how the mechanical constraints of the enclosure affect the material and your device's ability to seal under pressure and over time.
For today's session, we'll primarily focus on long-term applications. As a sneak preview, we'll hit on factors like gap spacing, ideal compression, compression force deflection, and gasket design and thickness. All these factors and a few more come together in your design to enable your seal to prevent ingress and maintain long-term performance. As we've said before, different types of foam materials are the gasket material of choice for electronic enclosures because, taken as a family of materials, they're conformable and forgiving. They compress more readily than solid rubber, firm plastic, or other choices.
But one reason enclosure gaskets fail has to do with improper compression ratios. Perhaps the first step in selecting the proper thickness of the foam material is to understand the range of the gap in the enclosure sealing surface and the possible range and thickness of the foam material itself. In other words, you must consider the tolerance variation in the enclosure's mating surfaces and the gap between them. And you need to consider the tolerance variation expected in the thickness of the foam. The question is, if a mechanical gap between mating surfaces is at the highest predictable space and the thickness of the foam is at its lowest predictable height, will the foam still be compressed enough to affect long-term seal?
If the gasket will have a layer of pressure-sensitive adhesive or other material layers, be sure to include the thickness of those materials in your calculations. Also, consider the surface texture of the enclosure's mating surfaces. Rough or uneven surfaces will require a foam that can compress and conform more effectively than would be needed for smooth or polished surfaces. For complex shapes or step surfaces, you may need an even softer, more compliant foam to adapt to inconsistencies while maintaining long-term rebound and sealing forces.
Obviously, the thickness of the foam gasket in the relaxed state must be significantly thicker than the final expected gap under compression. And although we recommend a minimum compression of 30% as a beginning baseline, there's no one easy formula to give you one answer for every circumstance.
But fear not. Rogers Corporation offers you a handy tool they call the Rogers Gap Filling Tool that helps you dial in the right starting thickness and the compression characteristics you need. Let's take a quick look at that tool on the Rogers website.
Once the gap is defined, selecting a material with the right CFD, that is, compression force deflection, is the next step. As a reminder, compression force deflection is a measure of the force required to compress the foam by a given percentage, such as 25%. It tells us how much force a gasket pushes back with as it is compressed. Here's an oversimplified table that you might find useful. When compressed 25%, if the CFD is less than 10 psi, then the foam is suitable for easy closure forces, as might be found in lightweight plastic housings. If the CFD is between 10 and 30 psi, the foam is suitable for a good balance between compression and sealing in mini enclosures. A CFD rating of 30 psi or higher would be suitable only for enclosures capable of applying high stress or high pressure, such as bolted metal assemblies.
A more precise way to look at CFD data is on a stress-strain curve. This stress-strain curve compares the CFD of two pour-on foams, the 92 formulation, which is very soft and easily compressed, and the 60 formulation, which is the firmest grade of pour-on foam. Both test specimens are 15-pound density and 0.125 inches thick when relaxed. Notice that to compress the 92 formulation by 30%, it requires only about 2 psi. But to compress the 60 formulation by the same amount, it takes more than 45 psi.
As you consider the CFD value of the gasket material you're considering, you can then calculate the amount of pressure your enclosure must apply to compress the gasket to the desired closed gap.
And Rogers offers another handy tool to help you create a stress-strain curve that's meaningful to your application. The compression force deflection curve tool can be found on the Rogers website. Let's take a look at how that tool works.
The relationship between compressibility and sealing performance is not linear. That is, we cannot say that the more easily it is compressed, the better the seal it will make. A softer material could need more compression to reach an effective sealing force than a foam that is firmer. In other words, if choosing a very soft foam, you may need to start with more material thickness and/or compress it more than if choosing a firmer foam.
Very soft foams are most effective when closure gaps are inconsistent and when compression forces are not balanced, as is often the case in door gaskets.
Okay, let's stop here. I think we've given you enough to think about for one day.
And we've shown you several available tools that we hope can help you make decisions in the selection of your gasket material. Please use them, play with them, bookmark them, and come back often.
And don't hesitate to reach out to us at Marian or the good folks at Rogers with questions. Use us as a sounding board to confer with your design work.
In the next session, we'll look at testing that helps you compare the expected performance of competing materials.
We'll also discuss the importance of reliability testing. Until then, I'm Jimmy Budd.
And as always, I'm Phil Taylor. See you then.